on method have been promoted by Panos, and I'm very happy to be with you today and to support this initiative. I think methods are changing quite quickly,
Sorry,
and they
I'm
are
trying
really.
to put it in the my headphones.
Alessia, maybe you can close the microphone. Thank you.
Oh, sorry.
So basically, methods are evolving, and so we, thanks to Panos, we are trying to involve some colleagues that are very expert in some new method because we want to share with you the possibilities we can do. And today, I think we are very happy to have Bart with us. And so I leave the floor to Panos, and I'm very happy to listen and to follow this seminar. Thank you. Enjoy.
Thank you very much, Alessandro. So it's my turn to welcome Bart. So Bart Vanneste is an associate professor of strategy in the Strategy and Entrepreneurship group at the UCL School of Management. He will tell us, but his main research is in corporate strategy. I follow his work. He has published in AMR, Organization Science, Strategic Management Journal, and other places. I also use his book with Vanneste in my teaching. And I have noticed of his latest paper where they are trying to create counterfactual outcomes using machine learning. So I thought, what a better speaker to talk to us about AI ML in management research. So the floor is yours, Bart, and thank you very much indeed for joining us today.
Okay, Alessandro, thank you very much for the invitation, and Panos as well for the kind introduction. So let me make sure you can see my slides. So yeah, they should be coming up now.
It's all good, Bart.
Perfect. So yeah, I'm very grateful for the invitation and also the topic, because it's the topic that is closest to my heart. So it's we're going to talk about machine learning or AI in management research. And I discussed with Panos that what might be a useful setup for this webinar is that I take about 30 minutes to go through some of the points I want to make, and then leave the remainder 30 minutes for Q&A and then a wider discussion. So when I talk about machine learning, I really have in mind data-driven AI. So it's a form of artificial intelligence where we try and solve a task by learning from data. And these methods have been developed over many decades, but they seem now to come together both in computer science and in other sciences, including management research. So I'll provide sort of a few applications where machine learning is currently being used. I'll draw heavily from my own work because that's what I know best. And the way I've organized this is basically by the different types of machine learning, or by the different types of learning problems that people typically focus on. So you may have seen an overview like the following, where they talk about supervised learning, unsupervised learning, and even self-supervised learning. So the idea is that machine learning is really about learning from data, but what you learn differs by these buckets. So in supervised learning, the data has an outcome, and the goal is to predict that outcome. So let's say you have a sample of firms, some are high performing, some are low performing. Then we build a model that sort of can tell us, hey, given these characteristics, we think this firm is going to be a high performer and this firm is going to be a low performer. So the structure of the data is such that you have a bunch of axes or inputs and an output, or a y, or a dependent variable. And the goal is sort of to predict that outcome variable given your inputs. Now, in unsupervised learning, the data looks a bit different in the sense it doesn't really have an outcome. So let's say you have a lot of employee data, you know a lot about your employees, when they joined, who they're emailing, what type of projects they work on, but there's not a real or a clear outcome that you're trying to predict. The typical goal in unsupervised learning is, given that data that you have about your employees, how can you describe how can you describe that data more compactly? So you could do some form of clustering. Say you have 1,000 employees. Can we sort of find buckets of employees, and each bucket contains employees that are more similar to each other compared to employees in different buckets? Or can you uncover some underlying dimensions that describe more succinctly the main characteristics of these employees? But the idea is here, really, you have like a lot of data and you're trying to come up ways to simplify that and to generate insight from that data. And the last one, self-supervised learning, is very, very prevalent now in the terms of generative AI. And it really sits in between supervised and unsupervised learning. So the data has no outcome. So it's not that you can say, well, I'm going to predict high performers, low performers. But the technique you're using is very similar to supervised learning. So the goal is to learn a representation of the data. So come up with a model that allows you to describe the data succinctly. And the way to do that is you're going to use the data itself to predict it. So I'll give some examples, but in the context of large language models, the way these models are working, you give a sentence and every now and then you leave out a word. And then the machine learning algorithms, its task is to predict that missing word. Now, if you do that many, many times, you create an underlying model that sort of has the ability to represent language, natural language, with a single model without the data having a explicit outcome variable. But you use this clever trick that every now and then you drop a word, feed the remaining sentence to the machine, and then the machine has to predict that missing word. And by that cycle, if you repeat that many times, you can get a model that actually has a nice representation of the data. So these are sort of the blocks that I'll go through, or actually I'll focus on supervised learning in the beginning, because that's closest to what we've done in the past, right? It's a regression, there's an outcome variable and some independent variables. And I want to see how these new ideas about machine learning connect to that idea of supervised learning. Then, in the interest of time, I had to choose. So I chose the remainder to focus then on self-supervised learning, because that's really underlying generative AI, and that's really booming these days. And I think that's where we will see the biggest changes going forward. So I thought it would be nice to have a discussion around these two. And what I do is, for each of these big blocks, supervised learning and self-supervised learning, I illustrate some studies or some papers that say, okay, here's some ways that it's being used, and hopefully that will give us some ideas where we can use it going forward as well with some new applications. So let's begin with supervised learning. So the goal here is to predict an outcome. A simple regression framework does a similar thing. You have an outcome, some input features. But now there's a key distinction between the way computer scientists think about it, or people who have developing machine learning algorithms, versus us social scientists. So in machine learning, you want to predict the outcome, but you're not necessarily interested in the marginal effects or the effects of an independent variable on an outcome variable. In contrast, in social science or management science, oftentimes what we're interested in is, well, if I change my input a little bit, what would happen with the outcome? So we're interested in the coefficients, not so much in the R-squared, right? So the R-squared would be predictive performance. The coefficient would be the marginal effect, right? And to push it even more, oftentimes we're not just interested in the marginal effect, but the marginal causal effect, right? So if I were to change it, then what would happen with the outcome, right? Now, I think this is a very different approach, but what I'll show is some methods that actually combine both approaches, right? Where you say, how can we use these predictive techniques while still trying to get these marginal effects or causal effects that is so typical of our research. So the first application has to do with variable selection. So if we say we want to know an effect of how an input affects an outcome, usually we want to control for a whole bunch of alternative explanations or variables that we don't think are different than our key explanation. Now, one way of doing that is to pick control variables and include those in your regression. There's a question of which control variables should you include, right? So one approach is, let's say, let's account for all the theoretically relevant variables that we can think of. And that might be a good approach. But what you're seeing these days is that oftentimes our data sets are getting bigger and bigger. So we may end up with tens, if not hundreds of possible control variables. Even if we have a smaller number, it doesn't necessarily tell us, or theory may not necessarily tell us which functional form to include, right? Because do we just include the linear forms? Do we include the linear plus the square terms, linear squared plus cubed forms? So there's a whole bunch of situations where we don't necessarily have strong priors on which control variables to include and which control variables to exclude. So Baloney et al., they've come up with some nice technique to think about using a data-driven approach to come up with a good selection of control variables. And what you see on the left is a single selection procedure. So that's basically saying, let's include all the control variables that are significantly predicting the outcome, which is maybe what we would do, right? We include everything that's relevant for the outcome variable. Now, what they show is through simulation work where the red bell-shaped form, smooth bell-shaped form is the true causal effects, and the blue bar diagrams is the measured or obtained effect through regressions. You see that these two don't nicely overlap. And they're making the point, if you do this single selection procedure, you are missing out on control variables that should have been included because they're relevant, they're correlated to the key independent variable. And the reason you're excluding them is because there's this correlation. Now, luckily, they identify the problem and at the same time give a solution. And that is the double selection estimator on the right, and the simulation results play out very nicely. And the point they're making is you should include two sets of control variable. The first set is those that significantly predict the outcome, and those that significantly predict the key independent variable. And then the union should be included in the final regression. Now, what's nice, and here's the link with machine learning, when you say they should be predictive of, that is really a machine learning question. So then we can use our machine learning methods to think about, well, how can we actually select these? So in a paper with my collaborator, Ranjay Gulati, we applied this approach, and I'm sharing it here just to give you a sense. So the first step is basically you regress all your control variables on your eventual dependent variable, and we're using something called the lasso, or regularized regression. In the second step, we're trying to predict the key independent variable, again with a lasso and a potential set of control variables. And then in the last set, we are taking the union and include both. So here you see where predictive or machine learning can sort of lead to a way that you can combine both, trying to come up with a good marginal effect estimation, but thinking about how we can use predictive methods. Okay, so the next paper that Panos briefly referred to is this new field around synthetic controls. And here the idea is that we have some firms that are treated and other firms that are untreated or deemed control units. Now let's simplify it a little bit. Let's think about one treated firm and a whole potential bunch of control firms. Now, what these synthetic control techniques try to do is make the treated and control as similar as possible in the pre-period. That is, in the period before the treatment is applied to one of these firms. Now, what we're using this technique together with Miro Sogrevand and Anil Doshi and myself. And what you're seeing here is sort of the outcome of an regularized regression technique, where we're trying to get this similarity in the pre-period as close as possible. And the key idea is that you want to weight the potential control firms in such a way that the lines that you see in the pre-period overlap as much as possible. So we're looking at an M&A between Family Dollar and Dollar Tree. And here you see how operating expenses fluctuates before and after the acquisition. And instead of saying we're going to give equal weight to all the potential control firms, you're saying, well, maybe there's a better way to weight these control firms such that the comparison is more like for like. And how that weighting scheme is arrived at is through a regularized regression, and that is all data-driven. Right? So again, to reinforce the point, we have a very typical management research question. How does an M&A affect operating expenses? And we're using machine learning to make the comparison more like for like than we could have otherwise done. And then in the next application of supervised learning is thinking about where do our hypotheses come from. So sometimes they come from outside the research context. Sometimes they come from observation in the research context. Sometimes they come from looking at the data of the research context. And that is a typical approach because we're oftentimes researching things or questions that we don't know the answer to. So the field is oftentimes giving us pointers of what to look for and what to expect. But we also know is that once we looked at the data for hypothesis generation, we cannot use that same data to test our hypothesis because then we run the risk that we'll report a lot of false positives, right? Let's say we have a data set with 100 that is describing 100 variables between pairs of variables. If we have a p-value of 0.05, that means even if in reality there's no relationships between any of these variables, through random sampling, 5 of the 100 will show up as significant. If we then write a paper on those 5, we find support in that sample, but it's just spurious correlation that we're reporting. So here's a paper by Shrestha and colleagues, and what they're doing very nicely is saying, well, let's make these 2 steps explicit. Let's have a step where we're looking at the data and generating hypotheses. So trying to find robust patterns in the data. But importantly, before we do that, we split the sample. So we do one part of the sample for induction, for trying to find robust patterns. Then we theorize about those patterns. That is, we come up with potential explanations for why that pattern may hold, or for theory. We derive hypotheses for that. We also derive additional hypotheses that are based on that theory, but are not necessarily the correlations that you observe in the initial sample. Once you've done that, you can say, well, let's now look at the other half of the data that we set aside. We can first test whether that correlation indeed holds in the new sample, but we can also test our additional hypothesis that we formulate. So there's a separation between hypothesis generation and hypothesis testing. Again, how these induction works, we can use machine learning techniques, right? To come up with robust patterns. We can use, okay, what are some reliable patterns in the data that are worth or potentially interesting theorizing about. So yeah, just to recap this point is, supervised learning is about prediction. We care a lot about causal effects or how inputs change the outcome. You can see multiple applications where these 2 actually come together very nice. So let's move to self-supervised learning. And yeah, I think it's very important or very exciting field because these are the technique that's oftentimes underlying most of the generative AI models that we see, especially large language models. So just a quick illustration of how this works. Let's say you have a sentence, Paris is the capital of France. Then what you would feed the model is 3 steps. You would say, Paris is the, and then you ask the model to predict what the next word is. And in this case, we know what the next word is, so we can tell the algorithm whether it's doing a good or bad job. Then from the same sentence, we say, Paris is the capital, And then again, we feed that part, and then the model has to predict off. And then lastly, we predict, or we ask the model to predict Paris is the capital of, and then the model should predict France. Now, this is self-supervised, or it's supervised in the sense that each time we're sort of giving it an outcome, but the outcome is not truly an outcome in the sense that that's what we're interested in. We're interested in the model that's being learned while going through these steps. Yeah? So once it's done with the exercise, we now have a nice large language model, which we can then apply in many different applications. A similar technique also works with images. So on your right, you see the nice, complete picture. And then on the left, you see the picture that's being fed to the algorithm and says, find the missing blanks or fill in the missing blanks for us. And when doing this repeatedly, there's a model that emerges that can generate images through this technique. Now, importantly, this self-supervised learning oftentimes is done for us. We don't need to engage in it. So the self-supervised learning that I was talking about previously, the synthetic controls, the data or the sample splitting, or the first application, every time we need to build that supervised learning model. Here is different. That self-supervised learning model is built by your OpenAIs, your Meta, by your Google, and so on and so forth. So they put in a lot of effort, and that's great. So we can benefit from what their models that have. Okay, let's see at some applications of how this can be used. And the first is a joint project with Raj Chowdhury and Shikang and myself. But we're interested in corporate communication. So we have some corporate statements from a sample firms, and we want to know how these for each of these 5 styles: excitable, stern, dramatic, rambling, and melancholy, to what extent they're present in the data. Now, before generative AI, what you would do is you would hire a group of research assistants and ask them, well, for each of the texts, could you rank them, right? So whether it's present or to what extent it's present. Now, what we've done is instead of hiring humans, we hired some large language models, and you can see on the right which one we use. So Claude, Llama, Mistral, and some from OpenAI. And we basically asked the same question, right? So given this text, can you tell us to what extent each of these 5 communication styles is present? Now, and as you would do for human RAs, research assistants, you would have some inter-rater reliability checks by including multiple RAs. So here we do the same. We use multiple LLMs, and here's some preview of the things that we're finding. So it's nice that actually the LLMs, they don't necessarily agree on the level, but on the relative ranking, they seem to agree quite strongly, right? So if you look at each and every, they're sort of ranked. Most LLMs have the same ranking for a given type of text. But again, you can just calculate those reliability statistics as you would for a for human respondents. So one approach approach for generative AI is just thinking about, well, can we use it to conduct measurements maybe on a scale or that we were not able to previously. So the next application is work with my colleague Anil Doshi, Jason Bell, Emil Mirzayev, and myself. And here we're not necessarily looking at measurement, but saying, well, can we study these systems in and of themselves? So the overarching question that we had is, wouldn't it be nice if you can use AI in strategic decisions? And there we said, well, if you look at supervised learning, that technique does well when you have a lot of data, because then you can use it to build your machine learning model and then to predict it for a new case. But strategic decisions are such that oftentimes you have very limited data, or they're unique to your specific company. So even if you have a lot of data from other companies, the extent to which it is relevant to your firm may be limited. So then we say, well, maybe this generative AI provides a solution, because That even works if you provide it with limited data yourself, because it already has been trained on so much data beforehand. So basically what we do, a similar approach as in the previous project, we ask quite a few LLMs to distinguish, or given a pair of business models, say which one it prefers. And so our strategic decision is basically which business model should we adopt. We ask multiple LLMs to do that. Each LLM, we ask it to take on different roles. So whether you are a CEO, an employee, maybe a customer, maybe a government official. And then also we play around with the prompt. So that's the text that you give to the large language model to assess or to provide an answer to. Given all that data, then we combine these AI evaluators in different ways. So the first way is we put all the evaluations of a single LLM, single role, and single prompt together. So these are sort of the uniform evaluators. Then we say, well, let's mix it up. So for the same number of evaluations, let's have some from different LLMs, some from different roles and using different prompts. And the last is, well, let's also put everything together. So not just the same number of evaluation, but mix it up and go bigger in scale. And we came up with 60 business models. We also asked human experts to rank these. So then we could see the extent to which the assessment of the LLMs agreed with those of the human experts. And this is roughly, or this is what we found. So basically we're comparing on 4 different outcome measures to what extent the LLMs agreed with human experts. And the comprehensive AI evaluator, mixed AI evaluator, and uniform AI evaluator all refer to the different combinations that I previously showed you. So uniform are the pure ones, mixed one is where it's mixed up, and comprehensive is mixing up plus scaling. And what you see is that the agreement is quite nice in the sense that for some correlation measures, you get around 0.5, 0.6, all the way up to 0.7. If you do a rank correlation, you're sort of around 0.4, 0.5. We had 60 business models, 10 different industries. Then we looked at, well, can we identify which it said was the best model per industry? And around half of the industries, if you take the biggest AI evaluation, is there's congruence between what the human experts say and what the AI says. And likewise, also for selecting the worst, potentially worst model in that list. Now, what we also did is ask some human non-experts and not people who are trained or have a background in strategy or business models. And their scores are listed in orange, the lower bar. And you see that most often the AI is on par or better, or in the sense of more agreement with human experts. So if we start to think about how can we use these systems, it seems that at least scope to explore this further, because they seem to at least capturing something that human experts are also capturing. Okay, then for the last example, I always like to go outside our own field. So I've talked about generative AI for measurement. I talked about studying generative AI itself as a research subject. Here is some example from chemistry for how to conduct research with generative AI, or large language models. Now, we know that, or there's a lot of discussion in our journals, can we use generative AI to write our papers or to copy edit our papers and so on and so forth. But here, these authors take it one step further. Can we sort of map out the entire pipeline of what it takes to do research, very much from the initial idea of, or from the initial step of coming up with an idea, searching the web for relevant documents, specifying the experiment, running the experiment, executing code with analyzing the data, and then also writing the paper. So here you see there's sort of, they call it this approach, or they call this system a co-scientist. And some of those parts, they have allocated to a large language model. That means a large language model has to take the first step on deciding what happens next. And they have given the ability or 4 potential actions that the large language model can do. Here's the planner. It can Google something. It can instruct to code. It can say what experiment to be run. In this setup, the experiment is still run manually, but still it's a nice one. And it can also search technical documentation. Now, I put this out there because I think also for our field, what we're increasingly seeing or increasing the questions are being raised, where does this generative AI fit in terms of the type of task that we are doing? And this is sort of showing one way in which this can be integrated. Okay, so let me just highlight some of the key differences between supervised learning, where you're predicting an outcome, and self-supervised learning, where you're drawing from a large model and then applying it in your own research. So a key distinction is with supervised learning, you are training the model yourself, right? So you are trying to find a function between an outcome and some inputs, and yeah, there's different algorithms, but the whole point is you deliver the data, you find that algorithm that works best or that works well in your context. Whereas with self-supervised learning, you can use existing LLMs, and sometimes, you know, they're very big, they work very well, and the training, they have just released some estimates of how costly they are. Some of these models, they calculate the cost of training them up to $100 million US, right? So that means that it's unlikely that these massive models we will be building. Instead, we can be thinking about how can we use those models best in our application. Now, the second point is related in the sense that because you're training them yourself, your application needs to have sufficient, or they work better with more data, right? So small samples also works, but the more data you have, the better it works. With self-supervised learning, given that you have already such a strong large language model, even if you have a limited data or small application, you can very, very well use these large language models. And then lastly, I try to map out some differences between the type of applications that we tend to see in supervised learning and the type of applications that we see in self-supervised learning. So here is sort of the overview of studies that I've been drawing out from. So I'll just leave it here. And yeah, I'll be happy to transition to the Q&A.
Thank you very much, Bart. Personally, I found your talk and presentation extremely insightful, and many things are new to me. So thanks a lot for covering such breadth in a short period of time. Let's open up the floor to questions. So please use your electronic hand so that we can keep some kind of order. Or if you like, maybe I can, until we have questions, I can preempt the Q&A session and say, I wondered, in your experience, what has been the reaction by editors and reviewers in the use of machine learning, either for the matching process or the other examples that you brought in?
Yeah, so there's sort of two that that come on top of my mind. One is some of these methods are not yet that well known in our field. So there needs to be a little bit of education happening in the review process, a bit more than you would do with well-established models. So I think that's reasonable, right? So you need to allow your reader to evaluate your work. So I think there needs to be, yeah, that thought process that the researcher may have gone through themselves. You need to share a little bit about, you know, where these methods are coming from and what they're doing. The second is, I think, you know, we might have a biased sample here by the title and by your introduction. We are very open to machine learning methods, but our field oftentimes likes to see utility. So novelty is not sufficient. In my experience, they really like utility as well. So I think other fields, novelty by itself seems to be a bit more sufficient. But here, rather than saying this is a good method, I think it would be very helpful or smoothen the review process if we can also say, well, this is how it helps us in this particular way.
Thank you.
There are also questions on the chat.
Oh, sure. Any reflections on research and ethics in connections to these applications?
Yeah, so I think the application that I showed, the research, I mean, they vary a lot, right? So I don't think there's a single answer for that question. So I think the supervised learning ethical implications are very similar to the ones that we have with a regression type of framework. So I think with those we tend to be a bit more familiar with. On the generative AI one, I think sort of there's two blocks, right? So are the models themselves, what type of biases or what of sort of ethical considerations they have versus given that model, what are sort of an ethical way of our applications? And on the first one, we are seeing that these models do have some biases, right? So when they generate text, text can be gendered or politically biased in one way. So I think these issues come more to the foreground for some applications than others. So I think with selecting between two business models, I don't think that's necessarily very prevalent. But if you're studying sort of like gender dynamics at the boardroom level, then if you start using these things, that should be taken more into account. In how to apply that, I think the norms are now forming, right? So what is acceptable use, what is not acceptable use? I don't think we have a good answer yet. I think across the discussion that I see is that transparency is necessary, right? So whatever you do, you have to disclose what you have been doing. And I think as the field progresses, I think we'll probably settle on some ways where we say, okay, for here, we're very much comfortable relying on it. And for other applications, maybe less.
Thank you. I'll go to Isabel, and then there is a question by Felipe in the chat box. So, Isabel.
Yes, thank you. So I'm very interested in what you showed in the beginning, where you had different texts and you analyzed the different texts. Instead of using a research assistant, you said you could analyze directly the texts. This one, yes. So what is the difference between the use of AI doing this and what it's more like typical content analysis of text, where you, for instance, take the same text that you are using with AI, you count the words that are in the dictionary of excitable words, let's say, and then you count the number of words, let's say, in the text, and that's your measure. You quantify it this way. What would be the difference between AI and the more traditional content counting of words, if I can say it like this?
Yeah, I think what you're describing is sort of there's two dimensions, right? So what is the method? Are we coming up with a dictionary and then asking, given that dictionary, how closely is our text aligned with that? Or do we rely on a broader statement, excitable, maybe give a definition, and then ask the evaluator to interpret the text given that definition? Then the other dimension is whether we let humans do that or whether we let an AI do that. And in principle, you could do both. I think the approach for without dictionary is nice, or is not, or one benefit is that it's very scalable, and you can ask it also questions for which you not necessarily have built the dictionary. Right? Because there's a lot of knowledge that goes into building that dictionary. And for some applications, those dictionaries are present. For others, they're not. So I think that's sort of the one trade-off that I see.
Okay, thank you.
The question in the chat box is, for analyzing qualitative information, for example, opinions or comments, is there an AI tool or type of learning that is better suited?
Yeah, thanks, Felipe. So I think the first step is to think about what is it that we want to get out of it, right? So is it some supervised learning application? Is it an unsupervised learning application? Is it sort of a self-supervised learning application, right? So that should be the first step. And then you can think about, well, what type of algorithms can we use? So in this project, let me see, this project, for example, that we did. So I'm showing you here operating expenses. What we also did is for all these firms, we downloaded tweets that mentioned those firms before and after the acquisition. And then we inferred sentiment and then try to see whether the sentiment of the target and acquirer changed differently from those firms that didn't undergo an acquisition. So the way we applied it there is we used another data set for which there was already labeled data. So you had tweets and saying whether it was positive or negative sentiment. We trained an algorithm, and then once that algorithm was trained, we applied it to the tweets in our sample, and then we tracked sentiment over time. So in that application, our initial step was supervised learning. We used another data set, build our algorithm, and then apply that algorithm to the tweets in our sample.
Thank you very much. There is another question about international journals, how they have dealt with the use of AI and machine learning as a way to analyze data and research. I guess this is perhaps related to a previous question, but you may have something to add.
Yeah, so Andrew, thanks for that question. So I think what I'm seeing is two types of papers that use or apply machine learning, and type of papers that study the phenomena of AI. And I think your question is mostly about the first. So I'll answer it from that way. I think transparency is key, right? So if you think about this approach that we used with Ranjay Gulati, is we spelled out exactly what we did in each step so that it was replicable, right? So we were transparent and was replicable. I think for all the other methods, for this one as well, what we're doing is in the working paper, we're providing the exact prompt that we use. We're providing all the data that came out. We're providing all the reliability characteristics. So I think it's important that we sort of unpack the black box, right? So if it's just data in, answer out, I think that's going to be hard for a reader or a reviewer to evaluate. So I think, again, there we need to help them think through, okay, how is this research being produced and what is potentially the utility of this approach? So I think that's sort of in now, especially when sort of these approaches are being discussed or formed and the norms are being established, I think transparency and just being very clear about the steps you're taking is important.
Thank you, Bart. Do we have any other questions? I have a question relating to management research that has been floating around for some time, which is like our new PhDs will be trained in these kind of techniques and methods. And I was thinking about people that have been trained in terms of propensity score matching and maybe the use of QCA for more qualitative features. What would be the best approach? Is it about partnering with experts in the techniques or training ourselves in these kind of methods? Do you have any views on that?
Yeah, so it's sort of two ways. I think for incoming PhDs, this becomes part of the standard toolkit. Right. And then oftentimes we see, well, most of us, we specialize in some techniques more than others. And then that informs how we form collaborator teams, right, where we sort of each bring our unique expertise. But I think just as we were trained in propensity score matching while doing the PhD, these techniques are becoming standard for during a PhD, right? So you need to know supervised learning approaches, splitting the data, hyperparameter tuning. I think there's no way around that. Now, the extent to which oneself uses that in their career, that of course is a question. You can do it yourself or relying on a collaborator. And I think it's perfectly fine to rely on a collaborator, but I think the newcomers have no choice but to invest a bit of time in these exciting techniques. Yeah.
Thank you. Do we have any other questions from the floor?
Yeah, I see Catherine asked for the slides, and I'm happy to share them. So Panos, I'm not sure what the best way it is. Shall I just send them to you and then?
And then we will
Perfect. Yeah.
make them available. Okay, if there are no further questions for Bart, please joining me in thanking him for sharing his insights in an ever-increasing, ever important topic in management research. So we are very privileged to have you, and thank you very much for sharing with us your insights.
Thanks so much.
Thank you very much
Thank
indeed.
you.
The session has been recorded and will be made available on YouTube. Alessandro, do you want to say anything before we close?
Just a big thank to Bart, obviously. Eventually, I don't know, Bart, if there is any course, if there is someone that want to improve his abilities with these topics, if there is a course that you recommend or a book that you recommend, maybe this could be useful.
Yeah, so shall I give the recommendations to Panos as well? There's a very good book and a very good online course that I can highly recommend.
Perfect, it will be useful.
Okay, great.
So thank you very much, everyone. And thanks to Lisa and Nicola for helping in the organization of the event. Thank you very much.
Okay, thanks so much.
Bye.